So what we're going to look at here today is an inductance meter. So getting it in frame, I've got an Arduino Uno. I've got an I2C display where I'm printing out the inductance being measured over here in microhenry. So it's measuring 749 microhenries. So how this works, you get the drawing like so, as the Arduino pings the inductor and capacitor, which are connected in parallel, and it rings. The signal then goes to a comparator. It produces a square wave out, which goes to the Arduino. There's a pull-up resistor over there. So that's what's happening here. So the Arduino takes the pin high, holds it high for 5 milliseconds, and takes it low again. This then rings. The Arduino looks at the pulse length, works out the frequency, and because this value is known, I'm using 1 microfarad, it can then calculate the inductance from that. And it then prints it out to the LCD display and also the serial monitor. So the wiring on the Arduino side looks like this. There's our circuit, and the cap, and the inductor. I've got a 1N4007 there, 150 ohm resistor, and in this case a 330 ohm. The output of the LM339 quad comparator. In case of my circuit, I'm using an Uno. So pin 11 is doing the pulsing, and pin 13 is reading the pulse width in. And then this is the same. A4 and A5 are driving the I2C to the display over there. So what we can do next, I don't think there's much to talk about here. I'm going to show you what's happening on the scope. We have got 3 scope signals connected. I'm looking at the pulse coming from the Arduino, which is over here. That's pin 13. So that's a signal. I'm looking at that point, I'm looking at that point, and I'm looking at that point on the scope. So that's the ring that I'm looking at, and here's a square wave out of the Arduino that I'm looking at the scope. And I'm also on the scope measuring the frequency of that pulse to verify that my code agrees, and I'm updating this once a second. So that's the long and the short of what's going on here. This is a 1 microfarad capacitor in parallel with the inductor, but I've also put a 1 microfarad capacitor across the 5 volt rail because I'm using USB 5 volts. There's quite a bit of noise on it, and adding that filtering capacitor across the 5 volt rail cleaned it up nicely. So that's something to remember when doing this kind of stuff. So why don't we have a look at the scope screen, talk about that, and then look at the code. Alright, be with you in a moment. What we have happening here, the channel number 3, which is set for 2 volts per division, is showing us a 5 volt pulse that comes from the Arduino. So that's where the code turns the pulse on. That's the purple line for 5 milliseconds. So as you can see, as it takes it high, you get some ring. The turquoise line is the probe across the cap and inductor. Then the yellow is the output from the comparator. So you can see that it measures a bit of ring there. After 5 milliseconds, it takes it low, and that's when the real ring happens. Now that's 200 millivolts per division. So we can see that that's almost a volt of ring that we get there. The output to the comparator, we also look at 2 volts per division. So we are looking at what is that? So that would also be, okay, so that's 3.3 volts that we're looking at. Alright. Now I've set up a measurement on the yellow trace. Let's look at the frequency. So that's 5.6 kilohertz, 5618 hertz. So now when we go look at the Arduino code, we'll see that that ties up with that measurement of the frequency that was measured there. So I think that pretty much wraps up what the scope trace looks like. You can see the pulse go high, you can see the ring happening, and the output from the comparator, which turns that ring into a square wave which the Arduino can measure as a pulse. So that's the story there. Let's have a look at the code. Alright, so here we have the code. So we need wire.h and liquid crystal.h. That's for the LCD, the driving of that. Its address is 27, 20 lines. It's actually a 2-line display, but it's okay. It still works with the 4. Here we have a variable. So we got frequency, capacitance, inductance, and pulse. Those are and they double words. So those are 4 variables. So initialize the LCD, turn the backlight on, set up some serial comms at 115/200 board. Pin 11 is the input for the pulse that we're going to measure the width, and pin 13 is the output where we're going to pulse the inductor to make it ring. Straight away what we do is we take the output high. Let's bring that image back in. It's probably not going to let me do that. So over here, digital write 13 high, so the purple line goes high over here. And as always, there's a helicopter outside. Anyhow, after 5 milliseconds, which is this period over here, it takes pin 13 low, and we get a ring. It then waits 100 microseconds to let the ring begin to happen and settle, and that then does a pulse in measurement, and it measures its pulse width over here. Now if it has measured a pulse, in other words pulse returned a value of more than 0, then it executes this bit of code down here. So here's our constant for capacitance, frequency is going to be the frequency in microseconds, pulse in microseconds times 2. So you're looking at the full period. Inductance is going to be the result of that. So we know the frequency. So over here, let's take that away. We do the calculation. Inductance is 1 divided by capacitance times frequency times 4 times pi. Then we get some results. So the pulse length, it's high for 86 microseconds. So it prints high 4 as a string, and then pulse as a measured period. Then it prints another string, frequency in hertz, and that agrees with what we measured over here on the oscilloscope. It's very close. This is 5.8 kilohertz. It then prints another string, inductance, and it prints the calculated value. Then there's a 10 millisecond delay. Then it sends the stuff to the LCD. So it sets the cursor to the top line, position 0, and it prints out a string, inductance. Then it sets the cursor to position 0 on the second line, and it prints the inductance, the calculated value from up here. It sets the cursor to the second last position on the second line. You've got 16 places, so that's 14, and it prints microhenry. Then it waits a second and it repeats the measurement. And so down here on the serial monitor you can see that happening, and on the video you saw this happening. So that's that. I'm enjoying this new scope of mine. As you can see, having a 4-channel scope is useful, and it served us well for this little demonstration over here of an inductance meter. Demonstrates inductive and capacitive ringing when they're connected in parallel. Now we can measure the period of the ring to determine inductance if we know the capacitance. And that's how an inductance meter works. You can build your own using an Arduino and a handful of components. And I think that is going to wrap up our little talk here. We are done. Thank you, ladies and gentlemen, for joining me here today. This was a nice project. We all learned something. We saw some interesting stuff, and we certainly have a good understanding of what's going on here. So thank you for being here, taking the time to watch it all the way to the end. Take care. We'll be back soon with more interesting and exciting stuff. Cheers, folks.